It's 12 o'clock and that's when we're supposed to be starting, so I'm going to get going. There's quite a few online right now, so thank you for your attendance. I really appreciate, we all appreciate your coming to this session on indoor air quality. I'm Ken Baker. I work with the Integrated Design Lab. I've worked here for almost 2 years now. I was one of the folks that helped found the lab about 18 years ago. So it's really a great pleasure to be here addressing you from the Integrated Design Lab down at the Idaho Water Centers. We're part of the University of Idaho College of Art and Architecture. If at any point in time you have a question, I'm perfectly fine with you asking that question. We may have time at the end for some Q&A also, but if you have a question, go ahead and we'll go ahead and let you ask that so that we can take it as we go along.
Could you hit the record button?
I need to hit the record button. And where is that?
It might be under more. Scroll to the right. You're recording. We're good.
I'm recording. Yeah, I thought I saw a red flash. Thank you. Excuse me for that, so move ahead here. So I have a few slides I just want to go through about the Integrated Design Lab, and I'll start out with saying right now there's Jubin, who's on the bottom left-hand side. He's gone as of last week. He got a really good job at a university back east, and so we're very happy for him. He did great work for the lab. Also across the bottom, you see 3 interns that we have right now. That was one of the major reasons for starting the lab, was to give architectural and engineering graduate students real-world experience, and we get to work with you. So the top 3 there is myself, Damon, and Dylan, and we're all online today too. So thank you again for being here. I want to give a really big thank you to Idaho Power, because without Idaho Power's funding and sponsorship, we would not have these sessions. Also, as you can see with the slide here, we can provide technical assistance for architectural and engineering firms in the Idaho Power service territory, and it's actually a very good deal for you. We have a phase 1, 2, and 3, and you can read this as you like, or you can just contact us after the session and we'll go through what the scope of work could be for you for your project. But we can provide direct assistance to you upon Idaho Power approval, and it doesn't take long. It takes about 24 hours to get approval from Idaho Power for this. So think about that. If you're working on a project and you need some studies like massing studies done, you just need some consulting, even consulting on energy modeling, daylighting, or just lighting lighting design, we can help with all of that. Whoops, excuse me. And then we have the Building Simulation Users Group, and tomorrow there's actually a session, Power over Ethernet, so you can tune into that too. We have a new website. It's the same old URL, idlboise.com. I think it's com. Anyway, you can go to that, and it's Dylan completely redid that website. It makes all of our resources much more available. They're updated, and you can get a hold of us that way. You can look into the Energy Resource Library if you want to check out some tools or some books. There's all kinds of resources on that on the website now. So please go to idlboise.com and check that out. Speaking of the Energy Resource Library, we have probably, thanks to Idaho Power, probably about $300,000 worth of tools right now, diagnostic tools that you can use in your buildings. If you have an existing building or even a new building that you want to do some studies on, we can help you out with a tool loan. It doesn't cost you anything. Idaho Power service territory is what we're looking to loan to at this point. But we've loaned outside the service territory also, because Idaho Power has told us once they bought the tools for us, they do belong to us. But I think it's a good deal for Idaho. It's a very good deal for Idaho. These are great tools. The only other place I know that has anything even close to this is Washington State and in Seattle. So the design lab does a lot of technical assistance. I've already talked about that. And again, thank you, Idaho Power, for enabling us to do that, but we can help with your building energy studies. And we are about energy efficiency. So let me get into the presentation. And as you saw, this is on indoor air quality. And I'll distinguish it a little bit from indoor environmental quality, but we're going to talk about both. And what I think is that indoor air quality is a subset of indoor environmental quality. And again, we'll get into that a little bit more. This first slide, Elizabeth put this presentation together a few years ago, and I've updated it here in the past a couple of years. But this first slide Elizabeth put out there just basically shows that this whole concern with indoor air quality goes back a long way, at least into the 1800s, when we started occupying buildings and working in buildings, both offices and production facilities and such. But this is about source not ventilation, but about source. If you have a source of contaminant in your building, the idea is to get rid of it, not to ventilate. So if you had a pile of manure in there, you'd want to get rid of that pile of manure. Ventilation is not very effective if you have a source of contaminants in your building. We'll talk more about this. And then there's another one from 1893, and it's just basically saying that we don't like to share odors with each other very well. It's just not something that we look forward to. But I will say, we do share air. And we have, and we always will. Whenever there are people in a space together, you're going to share air. Even when you're wearing masks, you're going to share some air, and that's just a human condition, and I think that's okay. But knowing that, since we are closed into office spaces, what can we do about that so that the air that we are sharing, we have good ventilation, we're not bringing in contaminants and such. We're going to talk about that in the next approximately hour. And then one more from Elizabeth, and this goes back to 1999. But this is kind of tongue-in-cheek. Only 33% increase in ventilation was required for adults a week after a bath. And the measurement, as you go back historically, 1936, there was a Harvard study, and they talked about OLF, or OLF, olfactory. And one OLF is a sedentary person in say, like an enclosed environment, like an office environment. And that was used in 36 in that study. That's what they came up with, and it's still used today. Imagine that. There's a lot about ventilation and indoor air quality that historically is very dated. We're starting to learn more now, and we're learning more. I think we're learning more or applying more in the last 6 months than we have for the last 60 years because of the COVID outbreak. And then a declaration of energy without a declaration towards indoor environmental quality, it makes no sense. And you will see, and I'm sure you have, in the energy codes. I've worked in energy codes since almost the onset, the 1989 ASHRAE standards, but mostly since 2000 and 2001 when we came out with the International Energy Conservation Code. But they've always had ventilation as part of those codes. Now, generally they refer to ASHRAE, and we're going to talk about ASHRAE Standard 62.1, but the international code, the IECC also references the International Mechanical Code. And January 1st, we're going to have the 2018 International Energy Conservation Code and the International Mechanical Code, so you can reference either of those also. ASHRAE just happens to be the more, how do I say this, educated standard, in a sense, in that actively pursue the ventilation. Not always, I will say, not always in the most productive way necessarily, but I think we're getting there. There's some new publications out from ASHRAE now, again, responding to COVID, that are very good. And so we'll talk a little bit more about those as we go along today. So this comes from ASHRAE and the standard 62.1, which is the ventilation standard for commercial buildings. And commercial buildings is anything above 3-story residential. 62.2 is 3 stories and less above grade, and that is for true residential buildings. But what we're talking about today are commercial buildings. And so this acceptable indoor air quality, I think this is interesting just to read, because when I read it, I start looking for who the cognizant authorities are. And so acceptable air quality is air which there's no known contaminants at harmful concentrations that determined by cognizant authorities, and with a substantial majority, 80% or more of the people, do not express dissatisfaction. So what I'm getting from this, and what is true, is we do surveys of occupants in buildings, and this 80% satisfaction level, or when people are saying, yeah, this is good. The air doesn't smell bad, basically, because that's what mostly we're relying on. Also, flow across our bodies, of course, because that makes a difference. And I do think you really do know when your air is fresher and when it's not fresh. So this is based on surveys and some authorities out there, and maybe we'll get into that a little bit more. This table is recommended ventilation rates, and it's historical in that it goes back into the 1800s. And as you can see by those first slides, the first 3 slides that I came out with, yes, we did get interested in ventilation in 1800s, because with the Industrial Revolution, we started occupying buildings and people started complaining. And we also had tuberculosis, which that on top, that TB, that's what that's all about. And we learned that, wow, if there's increased ventilation, there's fewer cases of transfer of tuberculosis. So the science was coming along then. Moving forward to where we're circling the red circles, we got an ASHRAE non-smoking and an ASHRAE smoking ventilation rate. And this is in cubic feet per minute. A lot of tables I'll point out are in liters per second, but that we're going to see today. But this is in cubic feet per minute. And for a smoking area in 1981, with that standard 62 in 1981, you can see that they wanted 60 CFM per person. And for non-smoking, it was down to, I mean, almost nothing. It was 5 CFM per person. So that made a big difference. I remember when I came to Boise back in '86, I worked for the Department of Water Resources, and at that point in time, the building that we were working in, they told me that they had just done away with smoking in the building in 1986, and that previous to doing away with the smoking, it only allowed people in private enclosed offices to smoke. But I also remember a couple years after that, because that wasn't a statewide edict, a couple of years after that, there was a fire started in our Capitol building, and it was because a smoker didn't get their cigarette out and threw it into the trash can. Now that fire didn't burn anything in the Capitol, but it was enough of a wake-up call that because of life safety, not the life safety because of secondary smoke or smoking, but life safety because of the fire, the state of Idaho then outlawed smoking somewhere around 1988. If you look on this slide over to the far right, we have ASHRAE 62.1 2019, latest ASHRAE that I can think of, and that does a lot more for ventilation than what we had. In fact, in 2004, ASHRAE updated its ventilation standards fairly significantly. They came up with 3 ventilation procedures that they didn't have before. They had an indoor air quality procedure, and that's prescriptive for mechanical, for buildings with mechanical systems in them for ventilation. And then they had a performance, they still do, excuse me, a performance ventilation rate procedure, and then for naturally ventilated buildings or non-mechanical ventilated, they have a procedure for that. So they're trying to cover all the different ways that you can do ventilation, you know, mechanically with a performance rating or non-mechanically. And then this slide shows us a little bit of comfort versus sensory load and ventilation. And I think it's kind of interesting. On the bottom is the ventilation rate. And as I told you, is in liters per second, no longer CFM now. So just a quick conversion here. I think 1 liter per second is like 2.1 CFM. So, you know, if I have 5 liters per second, it's just over 10 CFM. So when I'm looking at this and looking at the perceived air quality percent dissatisfied, remember I said they do surveys of people. That's how they find out how much air needs to flow through a space, an occupied space. And it really, you have to get up to around 10 on the bottom, 10 liters per second, before you get down to about 16, 17% of the population in a building or the occupants are dissatisfied. So at the red line up there where you have about 25%, that's actually at zero ventilation. So people are in some degree happy to be in buildings that aren't mechanically ventilated. But buildings, there is air leakage in buildings. Air leakage should not be construed to be ventilation because we don't know when and where that air is going to move through a building. But sometimes I suppose it can be satisfactory enough, and that's what that red line is saying. I think I mentioned this, but I also put up here humans were perceived as the source of pollution. Back when Harvard did their study and they came up with that OLF again, and there it is spelled out for you that couldn't understand my pronunciation, olfactory sense, basically. So it wasn't, and it still isn't a lot, it's getting more so, but it isn't a lot about indoor environmental quality as much as indoor air quality and just that nose hit, you know, that when I did a lot of residential research, we did a lot of studies, Bonneville Power paid for them back in the 80s and 90s, and I was going out and doing blower doors. We were doing all kinds of testing on ventilation testing on residences around the state of Idaho, or actually around the Northwest, but I was in charge of Idaho. We learned that the nose hit, the moment you walk in the door, you can tell when how home is being adequately ventilated or not, because if you can smell last night's dinner, it's probably not very well ventilated. And this is the energy ventilation tie-in a little bit here too, because the tighter we started building buildings, and in this case residences, the more you needed to actively use ventilation and have sources of outside air coming in, a known source of outside air coming in. So that nose hit is what we used to always talk about. This table from ASHRAE 62.1, now if you actually go into 62.1, which I have that here, you can see it, these usually aren't a lot of money. If you don't have one, probably should get one. Because there's a lot of good information in there. But this table shows you just one little piece of the full table that has a lot of different occupancy types in it. So this is limited, but it shows you, we put it up here because it shows you how you can determine ventilation rates according to ASHRAE 62.1. And over on the left, the people outdoor air rate, the area outdoor air rate, these are additive, and it looks at your occupancy and your square footage, and it gives you a method for calculating how much liters per second you should have, or CFM you should have per occupant. And it's in both liters per second and CFM, as you can see as you go to the right and look at the default values. These are default, so if you don't want to calculate it out per occupancy load, then you can go to default values for occupancy types. Then on the far right of the slide, the zone air distribution effectiveness. This is interesting, and it's also very valid, that every distribution system is not as effective as every other distribution system in heating, cooling, and ventilation. It's just that's just the truth of it. And so this gives you an effectiveness rate for different different ventilation system types. You can also look, I don't know if I have it in this slideshow, but there's also different contaminant levels like 1 through 4 of ventilation. So if you're in a lab, not like our lab, but a lab that's actually doing science, or maybe a welding booth, you might have a ventilation level. You would have a ventilation level 4, but in an office building, you have a ventilation level 1, unless you have a known source of contaminants that are regularly coming in. So, so this ASHRAE handbook is a pretty good handbook to have. It gives you some pretty good ideas. I predict that because of the onset of COVID, things are going to they already have been rapidly changing. We're going to see some big changes in just ventilation strategies that will come out with. And I would not doubt, but what they will be, some of them will be put into code, maybe as options, but they'll be put into code. This chart here comes from the Energy Information Administration. It's the federal government Department of Energy, and what it shows is for a typical building, and it doesn't say which kind, but they typically use office buildings, but for a typical building, this is the energy use breakdown. And you can see that HVAC, which includes heating, cooling, and ventilation, accounts for the bulk of the energy use in a building, 44%. And I think the point really with this slide is we haven't made much progress on the efficiency side with HVAC, where on lighting, we've just gone miles and miles. We've made incredible progress over the last 10 years, 20 years with lighting. So we need to let that technology move ahead, and it has. We know now, I mean, much more so what works. And if you have a question about that's a great reason to contact the Integrated Design Lab, because we can help you with that. But we know now systems that work for different occupancy types, and they're really effective at ventilating and efficient too. So is IEQ worth more than energy savings? So as you see now, I brought in the term indoor environmental quality, not just indoor air quality. And I think I said it earlier, I consider air quality a subset of environmental quality, because you can bring in outside air and it can hurt your environment, your interior environment, like last week, unless you do things to filter or whatever. But like last week, we had a notice on our computers, since we're part of the University of Idaho, that said that they closed down Moscow campus. Now, they closed down the Moscow campus because it was they were much like Portland at hazardous levels. I mean, literally hazardous levels of smoke in the air. The next, I think it was the very next day, we got another email and said they closed down the buildings because the filters plugged throughout campus. And so they had to close down buildings and work with clogged filters. The interesting thing about this, the clogged filters, is that filters on our HVAC systems were put there to protect the HVAC systems, not people. Now, I'm not saying that's the way it is today, but that was the way it was. That's why filters were put in HVAC systems, to protect the systems themselves. So I'm not sure that I talked about everything I wanted to talk about there. So there are potential reductions in health costs and absenteeisms and in workplace performance. We know that with indoor air quality, when it's high, then people are more productive. I'm going to show you a few slides about this. It could be worth, some studies say, this 2002 study says it could be worth billions annually. Everyone has to well, not everyone's going to, but we have to figure out on our own what value we would place on indoor environmental and indoor air quality to the occupants of our buildings and the productivity to what they produce. Yeah, I guess if everybody started working from home forever, that wouldn't matter as much, but I don't see that happening. I don't think that's going to happen at all. We're getting through this, and we're going to be back occupying buildings. We're in the water center now. So is it IEQ worth more than energy savings? Just keeping track of my time here. Yeah, if the annual energy costs are $1 to $3 a square foot, and operational costs, which are mostly the people that we pay to deliver our business, yeah, that's $80 to $600 per square foot. So you can see, if I were going to go fishing for money, I would fish in the productivity arena if I knew how to do it, more than fishing in the energy cost arena. But I don't know that we know how to most effectively fish in that productivity arena at this point. I think we're learning, and we're starting to learn more quickly, but I don't think we're there yet. And this is an interesting slide, and is IEQ worth more than energy savings? And it's talking about the avoided cost, or what we could save, I guess. 16 to 17 million avoided cases of common cold and influenza. What this slide does not tell you is how much ventilation you need to get that, but I do have a slide that's going to get you some information that way. So reduced allergies and asthma, 8 to 25% decrease in symptoms, sick building syndrome, a really large decrease in symptoms. So we do know from some studies that increasing ventilation, outdoor air, or treated air, filtered or treated otherwise, does help us physically in our buildings. There are fewer cases of people being ill. But, and I say but, and mean it, and I kind of said this a minute ago, our knowledge of indoor environmental quality is limited, and that seems weird that would be the case at this day and age, but it really is. We haven't been doing studies for that long, or intensive studies, or I would say we actually haven't been applying the knowledge that we've already gained, because a lot of this, again, it goes back, for me, it goes back into the mid 80s, and we knew about things back then. We found out things, and we knew how to operate residential buildings, and commercial buildings have typically been way ahead of residential buildings on the indoor air quality side, at least addressing indoor air quality. So we know about things. Some of the factors, though, that are correlated with perceived air quality include dampness, and there's where your mold comes in. And even in a dry climate like Idaho, or especially southwest Idaho, where we're in a desert, you certainly can have mold issues, and you certainly do. There are sources and places where there's moisture, and wherever there's moisture and there's a food source and there's a heat source, you can have mold. You can and do. I've seen crawl spaces of commercial buildings that are just going up, and the lumber, the TJIs for the floor joists were put in wet, and it's just a big white fur of mold. It happens. It happens, I think, more than we realize. And so we have to be careful with the materials we put into the building, and then how we operate the building, take care of that dampness. Of course, ventilation rate's going to make a difference. Building materials and sources. It's that kind of the pig pen effect that it's called. I know that's kind of a weird term, but I think you get the point. You know, our carpets are probably one of the dirtiest. I think they are probably they hold more dirt than anything else in our buildings, because we walk in with our shoes on. We don't take our shoes off to come in. Who knows where people have walked, right? So carpets are notorious for being very dirty, and having sometimes contaminants in them. It's not always contaminants. And, you know, there's also studies that show that people that have barnyards are actually healthier because they're exposed to more of these bacteria and even pathogens at early ages, and they get over it. So building material and sources. I think this is an area where we've come a long way. I remember when I built my house 17 years ago, I had to explain to the paint company that yes, indeed they did have a low VOC paint. And then a couple years after that, I was back in the same paint store, and they had a big sign, low VOC paints. You know, we sell them here. This is what you got. So we've seen that. I think more and more. LEED has really helped with that, and some of the other green type of programs with the indoor air quality piece. And then the indoor air chemistry is what you bring in. It's that source again that really makes a difference. You couldn't bring in a space like I'm in, a classroom space, and open a can of paint thinner and not immediately smell it and have that have it in the air. So things like that we got to be aware of. But it says not enough is known to prescribe specific control levels for contaminants or mixtures of many interacting contaminants. We do have manufacturer safety data sheets on most products so that we can look at. So the methods for indoor environmental quality are kind of few and simple. Source control, again, you know, don't bring a contaminant into the building in the first place if you cannot do that. Then task ventilation, just dilution is the answer to pollution, is what we have always said. And then there's this non-specific particulate filtration, and we're going to get into talking a little bit more about filtration in just a couple of minutes. I think I'm on time here. I think I'm fine. And I would encourage you, if you do have questions, to go ahead and ask questions as I go through this. No problem with that. But filtration is a pretty big deal, and there's some new methods now that are being used. Again, in response to COVID, we're pretty good that way, and we'll talk a little bit about that as we get through, because the last part of this slideshow is going to be more COVID specific. But when I say COVID, I mean viruses, and so it could be common cold or any virus that we could bring into the building, and people get sick. That's just a truism of life. So, ventilation rates and sick building symptoms. Let's get into this a little bit. And what we see here, and this is an actual study that you can look at the chart, but I put over to the side what the chart is trying to tell us, that ventilation rate dropped from 10 to 5 liters per second. There's an increase in sick building symptoms by 23%. But if you increase the ventilation from 10 to 25 liters per second, there's a decrease in symptoms by 29%. So these are actual studies that have been done, and citations on the bottom there. So we know that we know it's true that if you bring in fresh air, or you make that air fresh through some system, building system like filtration, that it does work, and symptoms go down. So we know that's true. And this is on the bottom of ventilation rate again, and that's in liters per second. And then the relative performance, and that scale is not really big, you know, 1 to 1.04. I just want to point that out. But basically, if you're ventilating at 10, you see where those lines all start. If you're ventilating at 10 liters per second versus 50 liters per second, your performance goes way up. And this is productivity we're talking about here, with performance with people. So people do respond to higher levels of ventilation. I actually think some of that, I mean, we're talking about 50 liters per second. That's over 100 CFM. I think some of that is just we're more comfortable with a little bit of airflow around us. We certainly feel cooler, probably cold for some folks, depending on what you're wearing. So you have to be careful about that. But you don't see you're not going to see an office building ventilating at 50 liters per second unless it's natural ventilation, and that's more of a possibility there, I think. Good ventilation improves decision making 5 to 20%, increases speed of completing tasks by 8%, decreases, and these are all, I mean, these are based on studies, decreases absences from illnesses by 3%, and these studies are usually done on one occupancy type, maybe two occupancy type, whether they're a call center or K-12 school or something like that. So we apply them rather broadly, just to put a caveat on that. But decision making and ventilation rates, and I do know this is true. When I worked at Water Resources, worked there for 15 years, and they used to have a schools person, and I actually went out with him one time. We'd take a carbon dioxide meter, and that's what this slide's talking about, carbon dioxide, and you'd set an alarm at 1,200 parts per million, and then he would do a little talk to the classroom about energy efficiency, because that's what we're about. And inevitably, this is a K-12, inevitably during that class, that alarm would go off because we would reach 1,200 parts per million of carbon dioxide. And you can see here, well, what that meant for students, and these were elementary school students usually, is that a percentage of them were asleep. You get above 1,000 parts per million, I know I get sleepy. And if you're feeling sleepy in your office, I'm sure it's not because you're bored at all with anything that's going on. It's because you're not getting enough oxygen. And that same thing, if you're not, you know, if you're not really attentive and paying attention to me right now, I'm sure it's because your carbon dioxide rates are really high and you're not getting enough oxygen in your brain. Sorry, I like to say that. But you can see by this chart, for some of the, mainly the higher level, the innovations, higher level of thinking, when you really have to focus on a task, you want air and you want fresh air. And the more that you have, the better you're going to perform, is what this is saying. I'm not saying a wind blowing through your building, but you know, 10 CFM per person, 15, 20 CFM per person wouldn't be overdoing it for that cognitive level to accelerate a bit there. I think I'm doing great on time. We're gonna have time for questions, so be prepared to ask. So I'm not gonna pay so much attention to the chart here because the chart really doesn't tell you a lot, but the information from the chart to the right is where I'm gonna focus. And basically a 400 part per million increase in carbon dioxide was associated with a 21% decrease in performance. On the other hand, 20 CFM, cubic feet per minute increase in outdoor air per person was associated with 18% increase. So that's fairly significant. And then a 500 micrograms per meter squared increase in total volatile organic compounds was associated with a 13% decrease in decision making. So we're talking about decision making. So it's this one is kind of interesting to me. The reason I really wanted to talk about it is the first bullet and the last bullet. So increase in carbon dioxide, we're all exhaling carbon dioxide, right? So basically, all that is that it's just a metric of how many occupants you have, how much carbon dioxide is in the room. So a classroom, a conference room like we're in now, except full of people, things of that nature, you need to increase your ventilation in those types of situations in order to keep the carbon dioxide down. But carbon dioxide is not really a pollutant, it's just an indicator of a lack of oxygen or a lack of good ventilation. On the other hand, that bottom bullet, the micrograms of increase in total VOCs, that's a source we've brought into the building. It's not just people exhaling, it's a source that we brought into the building, and we can do something about that. We can do something about that when we spec the materials for our buildings. So that's a pretty big deal, I think. And then this slide I really like because we're starting to get into the COVID thing, right? This is about the common cold, which COVID is cold, and before long, it'll be part of the common nomenclature, I believe. And what it shows is it's just amazing, I think. So what we're looking again at liters per second ventilation rate, and the top bar on the left, ventilation rate 1.3 liters per second, all the way down to 5.2, and look at the percentage of transfer of colds. The study was done in China, actually, in dormitories. But look at the reduction. That 5.2 is equivalent to 11 CFM, 5.2 liters per second, 11 CFM per person. If you have that, your incident of transfer of the cold virus goes down by 30, almost 30%, over 30%. That's huge. So ventilation makes a difference. And ventilation can be outside air, or it can be a combination of outside air and somehow treated, either filtered or some other methods of treating air to take particulates and viruses out of it. So that makes a huge difference in our health. I didn't know where to put this slide. It was in there, and I moved it around, but I thought, oh, well, I'll put it here. But it just goes along with associated infections. Legionnaire disease, I think Legionella, I think is interesting. There's 18,000 reported cases a year, right? It has greater than a 20% fatality rate. And if we have things like cooling towers, which we do, this is interesting, that bottom little piece tells us that the drift from cooling towers can travel over 100 meters. So even if you're walking by a building and you get a drift from it, I mean, there's still a chance you could get Legionella disease. But most of these, we're treating the water in there, and you can smell that when you go into the building a lot of times, especially if you get on the elevator. You can smell the stack effect and from the elevator and the chemicals that go into the cooling tower. So indoor air quality is part of a larger, I've told you this, indoor environmental quality problem. But really all this is showing is sick building syndrome. There's a sweet spot for air temperature in our building, and at 72.5 degrees Fahrenheit. That's the sweet spot. And if we get higher than that, temperature range gets higher than that or lower than that, then we have different either pathogens, bacteria, or viruses that grow. And keeping that sweet spot, keeping about there is a pretty good deal for us. Are we doing enough to support indoor air quality? Well, the conclusion, Elizabeth's slide here again, probably not. We do assume that code is going to provide, if we follow code, it's going to provide good indoor air quality. And I would say that's not true. Code, the definition of code that I've used and people that teach code is this the minimum that you can do, the minimum level that you can do to occupy a building. Now it keeps changing, and it does ratchet up some generally. I was going to say sometimes, but generally it does ratchet up. But it is still the minimum. And as we discover new processes, methods, materials, technologies, code tries to incorporate them. And really, the code's not ratcheting up so much as it is, I think, is following best practice, and that's what it should do. It should follow best practice. It shouldn't get ahead of best practice. But it's not the best practice for indoor air quality. I'll guarantee you, and neither is ASHRAE 62.1. It's not. You have to think out your building, your occupancy, what's happening in there, and what kind of air needs to come in, and how much of that air in order to keep your occupants healthy. You also have to think about the energy side of it too, because it does cost a lot. If we, in the wintertime here, brought in totally 100% outdoor air all the time, our costs would go up probably pretty significantly. And so I'm not saying that going back to that slide versus people costs versus energy costs that would equal out, but the energy would go way up and people would notice it for sure. So going on, achieving high indoor air quality efficiency. You can use energy recovery. So right now in the code, remember I said it was the minimum you could do? In the code, and this is ASHRAE and IECC, you only have to have a 50% effective air exchanger if you're doing energy recovery, and some buildings are, some processes are, that process is required in some occupancy types, or when you have enough of a load on a building. Otherwise, energy recovery can be required, but it's 50% as the recovery effectiveness. When there are, there are very good heat exchangers out there that can get into the high 80s now. Think about that, the high 80s, and you see DOAS is one of the bullet points down here, dedicated outside air systems. If you do a dedicated outside air system and you have high efficiency heat recovery, what we showed, what Charlie Stevens showed in the study he did for Northwest Energy Efficiency Alliance, is that you could save 40, these were on existing buildings, they could save 40 to 60% of the total energy on those buildings. Because when you get up, and they were measuring 86 and 88% efficiencies out of these heat exchangers. When you get that high in a climate like ours in Boise, Idaho, you don't need to reheat and recool your air. You can bring in almost unlimited outside air, and you don't need to reheat and recool, or it's very, very, very small, because your effectiveness of that heat recovery ventilator is there. So those are out there, just so that you know that when you're doing your next design. So allowance for intermittent occupancy, and we call it dynamic ventilation control, however you want to call it. The natural ventilation works. Air treatment as a substitute for outside air. Air treatment is still ventilation. I take a little exception, but I'll change that slide. But now Damon attended an ASHRAE session here a couple of weeks ago on needlepoint bipolar ionization, and he said that's available online. Contact us or contact Damon if you are interested in hearing about that. He's been real impressed with it. We've had one of our research assistants looking into it and actually doing a literature review on it. So we'll know a lot more about that soon. And then you got the 62.1, which again, I think is a minimum that you should be using for all your buildings. Achieving high indoor air quality, we already have the USGBC, and they have a standard for that. And there's also a European standard, the CEN, that's a European standard, as well as ASHRAE 62.1. There's demand control ventilation, if you want to save energy for sure, but I'm going to show you another slide in a minute that says, for now, for people occupying buildings after COVID, you might want to just, reset to demand control, turn it off for now. Then there's natural ventilation, and of course, low emitting materials. Integrating IAQ and energy efficiency. Again, IAQ is reduced code ventilation rate. It doesn't have to be. Again, the code's a minimum, so you don't have to go by code. You can go by. Let's look at best practices for ventilation, right? And Elizabeth said, real effort goes into energy efficiency, and hell, I've been working in energy efficiency for 38 years, and I say there's still not enough effort in it. But then having one doesn't necessarily take away from the other. It's thinking things through and using best practices for your building designs. All right. This is from ASHRAE. There's a commissioning guide for indoor air quality, and I'm not going to go through all of these. Let's see, it's 1249. I'm not going to go through all of these because I'm going to get into the COVID stuff here. And these are contaminants that we know, VOCs that we know. Again, I do believe this is one area where we've done better over the years. This whole movement towards green has reduced the VOCs. I don't know how much, but that would be an interesting thing to do a literature review on also and find out. But I know it's practically it's gone down. And then limiting contaminants from indoor sources. And this is stuff that you should know about. A lot of this stuff has been used for a few years now. And there's some advanced design approaches we already talked about, dedicated outdoor air systems, and I'm not going to go into that. Again, I want to get into the COVID, which we are there. So ASHRAE has put out a guide now on COVID and HVAC, and it's actually, I think it's pretty good. I want to just go through a few of the things they talk about. It says basically what we've been talking about: increase outdoor air ventilation or filtering, disable demand control ventilation. Now, you don't need to do that forever. And if I'm in a space like I'm in now, which is a room where there's two of us in here and there's a big space, we don't need a lot of ventilation, and that does save energy. So you gotta think some of these things through for your particular building. Further open minimum outdoor air dampers as high as 100% if you're really worried, that you need a lot of airflow, and you may. What it doesn't say here is to measure your airflow, and I think that's the first critical thing that you would actually need to do. You need to know how much outside air is coming in, because typically we don't know that. That would be the first thing I would do. And then improve central air filtration to a minimum MERV 13, because we know that the MERV 13 filters, well, that's when we start to take viruses out of the air, okay? If you could go to a 14, that would be better. Let me talk about that though. High MERV filters. You can't just go into a building and do this if your system wasn't designed for a high MERV filter. You're going to add resistance to the airflow, increase pressure in the duct system, and all these things that are listed here. Comfort problems, freeze the conditioner coil, damage the compressor, crack the heat exchanger. There's a lot of reasons that you need to know if you can actually put a MERV 13 filter into an existing system. So you don't just do that. You work with an engineer that knows what they're doing that way and can actually measure the flow across the coils. But if you know it, then putting in that filter is a good thing, because starting with MERV 13, you're gonna filter out a percentage of viruses. And what was I reading the other day? It's real interesting. So if you take someone that has thin hair and one piece of hair, and you cut that in half, took that half, cut that in half, took that in half, cut that in half, you'd be getting down to the level of filtration that a MERV 13 filter does. So it's pretty small, but it catches more bacteria than virus. Keeps systems running long. This is kind of like a flush out, overnight if possible. Something like that. So when you come into the building in the morning, it's been flushed out pretty well, and things might build up contaminants, from people or whatever during the day. But yeah, here's another one that they came out with: consider portable room air cleaners with HEPA filters. And I want us to look into this a little bit more. I went to my dentist here a few weeks ago and get my teeth cleaned, and they had one of these in the room where I'm getting my teeth cleaned, and I'm like, yeah, studies have shown basically if these what air are they taking? Are they doing the whole space? No, studies have shown that they might just do a small part of a space and filter a small part, and not really get to what you're trying to achieve out of them. So I think just, if you're going to do that, look up what size you need, because size is going to be really an important factor. All right, and then consider ultraviolet germicidal irradiation, and I believe that's what they're doing in the water center right now. I believe that's what I heard that they're doing. So that works. Then relative humidity does make a difference. So we're a drier climate, and we don't usually put humidity into our buildings, even though we are drier climate. You know, it's just the occupants, you know, my exhales put humidity as well as carbon dioxide in the building, but it's still a dry climate. And what we want to be, ideally, is what we're trying to show here, is between 40 and 60% relative humidity. And this is a different chart, but we've talked about this. I've talked about this for 30-some years now. 40 to 60%, 50% relative humidity being the best, because on the right-hand side of this chart, you know, if you get too high, then you have bacteria viability. You also have fungal growth, mold, things like that. And if you get too low or too dry, you have more viral growth. Which the other thing that's interesting, because we talk about these droplets, you know, when I'm speaking here, right now, all these droplets are going out. I'm sorry to give you that visual, but I'm sure it's true. They're larger droplets in a low humid environment, and they last longer. they might go to the floor, but they last longer. So as you get around 40 to 60%, the size decreases, but they don't last as long. So it's a good thing. You're more effective on the bacterial and the viral side when you 40 to 60%. So this is my last slide, other than thank you slide, is 1256. Not a lot of room for questions. So maintaining poor indoor environmental quality can still use a lot of energy. Okay, it can. It can cost quality of life and productivity. If everybody could just work outside, except for fire season, it would be just great, right? So when you find clean air, just do some. I'm serious about this. Some full breathing exercises, some deep breathing, and that's very good for you. We can do better with basic IEQ measures like ventilation, moisture control, material selection, but it says that knowledge has not penetrated far into practice. I'm always an optimist. I've always hoped that it's penetrated farther into practice, and maybe it is, because again, we've been talking about this for, in my experience, I've been talking about this since 1986. We've known from studies on buildings that this is true. There is little overlap in the energy and IEQ worlds, but I think there is. Codes have been much better about bringing that overlap. And then process and tools are needed for design, and that's very true. And the Integrated Design Lab and Idaho Flower, with our programs, we can help with a lot of this. So contact us when you're going to do a building design. That's my presentation for today. I hope you got something out of it, and thank you on behalf of Idaho Power Integrated Design Lab. We got a little polling up there, so please do that. Please do that. Please fill that out, and we'll see you for the next session. Thank you for being here. Appreciate it. We had a couple of minutes if you did have a question. Was there?
Hey, Ken.
Yes.
There was a question from Jeff. He wants to know, when did HVAC systems start being designed with filtering built in mind to protect personnel, not just the equipment?
I don't know the actual timeline on that. It's a great question, though, because I wondered the same thing myself just this morning, because I was reading and I read that, and it's like, oh, that's very interesting. I would say probably about that timeline of the 70s, when we were worried about smoke and smoking. When the first standards came out for ventilation, 73 is when that happened. So I'd say that was probably the timeline.